All right, guys, trying something new today. Obviously, I'm going to make an answer key, but in case you want to see where I'm getting some of my answers from in a little bit more detail, I'm going to try and show you in one go. So if I make mistakes, you'll obviously see them corrected on the final answer key that'll get uploaded to Drive, but here we go. First off, as I go through, I've highlighted some key words like change in momentum. You know that change in momentum and impulse are going to mean the same thing. Just see how many times this comes up, right? In fact, it's one of these enduring understandings over here. So let's start off with multiple choice. Units of impulse are both A and B. In case you were stuck on that, that's because impulse is force times time, so that's newtons, times seconds, so check A. But it's also equal to the change in momentum. And momentum is in kilograms for mass, times meters per second for velocity, so also check. A and B are both units for momentum. Kilogram meters per second, just for fun, is actually what a newton is, because that would be mass times acceleration equals force. But that's neither here nor there. Okay? So, question 2. Which of the following can determine the magnitude of the object's change in momentum? That highlighted word means impulse. And I highlighted magnitude as well, because even though magnitude's an older vocab word, people tend to get this one confused. Magnitude means the size of the number, regardless of direction. So, let's process of elimination here. Mass times acceleration is force. That is not impulse. Impulse is force applied for a unit of time. So that's B. And I know this gets me the magnitude. It gets me the number of newton seconds, but it doesn't get me the direction. The direction would be given by the direction that the force goes. Hence the arrows in the equation up above. Whatever direction the force goes is the area the impulse goes. Direction the impulse goes. Womp womp. Okay. But thinking of area, this is a question that's getting at the objective of using a force-time graph to get impulse. So, in this problem, I would get the impulse by taking the area under the curve of a force-time graph. This irregular force causes it to accelerate, so increase its impulse, so increase its momentum for 9 newton seconds. Using the rectangle formula, it has -8 impulse in the next few seconds, making it 1 newton second total. But if the impulse is 1 and the change of momentum equals impulse, well, womp womp, that's also 1. Neat. Okay, so now, what is the product of an object's mass times velocity? Well, mass times velocity is momentum. Your momentum points in whatever direction the velocity goes. So 5b. The greatest momentum would be the one with the biggest product of mass times velocity. So A's momentum is 8, B's momentum is 15, C's momentum is 8, D's momentum, oh man, can't do that one in my head. Does that look like 95 to you? I'm pretty sure that answer is D. So, in this case, which involves the greatest change in momentum? Change in momentum would be any time that the mass or velocity changes. In all of these cases, the velocity doesn't change except for D. A goes at constant speed, B goes at constant speed. Terminal velocity means constant speed when falling and gravity is canceling out drag, so these go at constant speed. Momentum is neither increasing nor decreasing, so it must be D. So, fun fact, I'm pretty sure I did this wrong. So it's not 95, it's 9.5, making answer 6B. Okay, number 8. This is a momentum question that has to do with proportions, our skill from last unit. Momentum is mass times velocity. So if you double the mass, that doubles the momentum. If you double the velocity, that doubles momentum. And together, you have 4 times, 2 times 2, the original momentum. So the momentum quadruples. Answer B. 9 is asking a tough question. It's about bounce. You'll see these come up again later. In this case, the momentum of the ball is going to be different before and after because momentum includes velocity. So the momentum is positive to start and is negative at the end. It can't be A. The magnitude, remember that keyword? I think I highlighted it in blue before. Let me do this one more time. Magnitude means absolute value. So the magnitude of momentum, if I ignore the direction, it doesn't get bigger. It doesn't get smaller. The magnitude is the same before and after because the mass times velocity is the same if you absolute value it. So all of questions 10 through 12 deal with this situation over here on the right. We have a billiard ball hitting a billiard ball. This is a kind of trick question. The momentum of each ball is not conserved. Only the total is conserved, so 10 is C. Because think about it like this, and we'll use 11 as an example. The marble will slow down, so its momentum gets lost. Its momentum is not conserved if you just deal with one object. Whereas the billiard ball gains momentum. So its momentum on its own is not conserved. Momentum is conserved when you consider both objects in the collision together, hence total. Okay, so number 11. This means the momentum of the billiard ball increases, check. The momentum of the marble decreases, check. 11 is C. The momentum of the marble will transfer to the billiard ball, speeding it up. But since it transferred momentum, the marble will slow down and might even reverse direction. But if they're equal masses, this behaves like a Newton's cradle. And with a Newton's cradle, the momentum of the cue ball gets 100% transferred to the momentum of the other ball. Let's call this the 8 ball. So then afterwards, the velocity of the second ball after the collision is just 2 meters per second. Think like, what would it be for a Newton's cradle? The cue ball would stop, the 8 ball would pick up its momentum, the total momentum would stay the same, therefore same velocities. Now the speedy ones. 13 is A because it's an inelastic collision if they lock bumpers. 14 is B. The floor and the ball start apart and move apart separately. Same with a bowling ball and pin. That was actually the example we used in class. In super elastic, we did the astronaut wrench one in class together as a super elastic collision. 19 through 20 are also super elastic collisions. I can tell because my objects start together and move separately. There's that keyword magnitude again. After they push apart, their final momenta are equal in magnitude and opposite in direction, B. Magnitude shows up a lot because sometimes it's important to consider the direction, and then we have to specify the difference. Now, why are they equal and opposite, you might think to yourself? Well, let's pick some numbers because we are given masses ratios, but we are not given speeds. But their initial momentum is 0 because they're at rest. And I'm going to pick a random number. Let's say that after the collision, A has a final momentum of negative 20. That must mean B has a positive momentum of positive 20 so that it sums to have a final momentum of 0. They're equal in magnitude and opposite in direction because they each experience the same force for the same time, experiencing the same impulse. So they each experience the same change in momentum. Now that doesn't mean they go the same speeds. Obviously, skater B, being smaller, will go faster than skater A. That crosses off A and B here. And the ratio of speeds, well, is the same as the ratio of their masses. It doesn't go 3 times faster. Ooh. No, there we go. It doesn't go 3 times faster because A is not 3 times more massive than B. A is 1.5 times, or 3/2 as fast, or as 3/2 as massive, so B must go 3/2 faster. Okay. 19 then, they experience the same magnitude impulse as I mentioned before because they experience the same force in the same period of time. So equal magnitude impulses. The reason magnitude is important here is because actually A has negative impulse, B has positive impulse, but their magnitude of impulse is 20, so that's equal. In general, impulse is calculated by multiplying force by time, making it have units of Newton seconds and causes a change in momentum. By applying a force for a certain amount of time, you could speed up or slow down an object, causing it to change velocities and therefore momenta. Just like speeding right along. Right. So that means the fastest way to do this problem. If I want to find impulse, I can do force times time. That's 12 newtons of force for 5 seconds of time, and that's 60 newton seconds of impulse. But impulse, as we just mentioned, causes a change in momentum. Let's think initially about this wagon. Initial momentum of this wagon is 0. It's just sitting there at rest. The final momentum of this wagon is some sort of positive number. By applying a positive 60 newton second impulse, you've added 60 newton seconds of momentum to your wagon. So the final momentum must be 60. And now I can just solve backwards for V. If you want an equation precisely from your equation sheet, I suppose you could use this force times time is equal to mvf minus mvi. And that totally works because that would be 12 times 5 equals 30 VF minus 30 times 0, getting a final velocity of 2 meters per second to the right. Positive because you added momentum by having a positive impulse. You added momentum, so it speeds up. Positive. Now for the graph. This is method 2 in calculating our change in momentum, calculating our impulse. Notice right off the bat that A and B are the same question. So if I answer it for A, for B, I can just say samesies. 22A, A, without doing any math, produces the bigger impulse because A has the larger area under the curve. And so if the wagon, 12 kilogram wagon, were at rest and I applied impulse A, it would be going faster than if I applied impulse B. They both produce this, A produces the larger change in momentum because it had the bigger impulse, the bigger area under the curve. So between A and B, I kind of just mentioned this, A results in a larger impulse, so a larger change in momentum. Just like in this cart problem up here, the larger I make my impulse, the larger the final momentum. Well, if A's momentum is bigger, then A is going faster. A would be larger impulse, larger change in momentum. So faster final speed than B. Finally, last important skill for graphing, being able to graph equivalent impulsed trials. C experiences the same impulse but over a longer period of time than B. I'm not going to explain this precisely, but double check my work here. Before, the force was 32.5 newtons. Now I'm making the force about 25. I'm making it about 25% less. If I have 25% less force, I can do 25% more time. So 25 newtons, 5 seconds of time. Double check my work. Does that give approximately the same area as having 32.5 newtons for 4 seconds of time? I don't know. You check. Different graph here. Force times time graph I can use to get area under the curve to get impulse. But this graph uses velocity and time. Please notice that these are not the same graph. But I'm still asking about impulse. I know I can't use force times time. I know I can't use area under the curve because it's the wrong type of graph. So to figure out the larger impulse, I'm going to find the larger change in momentum. I'm going to use method 3. The impulse momentum theorem says that whichever one has the larger change in momentum must have the bigger impulse. So if they each have the same mass, whichever one has the larger change in velocity wins, or at least has the larger impulse. I don't know if they actually win. So think to this problem as whichever one has the largest drop in velocity, change from final to initial, the largest drop in velocity has the largest magnitude of impulse. And this picture is going to be for a little bit later. So from A, it goes from 5 to -3. This one has a delta V. It loses 8 meters per second of velocity. Oh, well, B is boring. B only loses from 3 to -2. This only loses 5 newton seconds, or 5 meters per second. I'll put more detail in later so you don't just watch me write. A has the larger impulse between A and B because it has a larger change in velocity. It loses 8 meters per second of velocity. That means if it stopped, like in the picture here, so now we're ignoring case B and just looking at the stick picture to the right. If the ball didn't bounce backward and it just stopped in 2 seconds, that means the change in momentum would be smaller and experience less impulse because now it's going from 5 meters per second to rest. Its change in velocity is only 5 meters per second. So then the impulse would be smaller than when it bounced backwards. Main idea here, and I know we did this in the very first lab of the unit, but just in case you forgot, things that bounce have a greater impulse because it requires a change in direction. Things that stick require less impulse because you only lose from 5 to 0 as opposed from 5 to -3. Last graph question, at least directly having to do with impulse. In this problem, we are trying to get the value of the impulse. I have the correct graph now, so hey, let's just take area under the curve here. It is a triangle with a base of 0.1 seconds and a height of 150 newtons. Therefore, this is something like 7.5 newton seconds. That means this ball was originally moving to the left at -5 meters per second, and you're adding positive momentum to it. Maybe the ball will stop. Maybe it'll start to go to the right. Let's find out. We would want to figure out the final velocity by drawing a before and after diagram. You know how to do these. In this case, before the collision, this tiny soccer ball, 0.45 kilograms, is going -5 meters per second to the left. An impulse occurs. And now we don't know what it's doing. I'm going to put a v to the right. I don't know if that's right, but I'll check it later and we'll find out. Using impulse momentum theorem. Impulse increases the momentum. So if you added 7.5 Newton seconds of momentum, the final momentum we could find, because we know the initial momentum was 0.45 times -5. And please note that's minus a negative, that's going to be a plus, but I still need to add it to the other side. Wow. The final momentum of this soccer ball, let's make that consistent. It like switches from soccer to tennis halfway. Let's make this soccer. That would be like a nearly 1 pound tennis ball, so that doesn't sound right. But anyways, this means the final momentum of this ball is 5.25 Newton seconds. The final momentum of this ball then can get us our final velocity. If there's 5.25 Newton seconds of momentum and the ball has a mass of 0.45, the final velocity is about 11.6 meters per second to the right. For collisions, one thing I want to point out is I'm going to answer assuming that this means magnitude. This would be a really boring and bad question if we didn't say that these were all magnitude. So please read this as which car experiences the greater magnitude of force? Magnitude of acceleration, greater magnitude change in momentum. And the reason I say this is because the green car has a positive force, acceleration, momentum, and velocity. So green car would have all positive numbers. Blue car would all have negative numbers. If I leave out the word momentum or magnitude here, then that doesn't make sense because I would be all green. Boo. So let's assume there's a magnitude. That means that both cars experience the same force by Newton's third law, the same impulse, the same change in momentum, and the same time. During a collision, force, impulse, change in momentum, and time are always the same. That's any collision. But whichever one has the lighter mass has the greater acceleration, and whichever one has the lighter mass has the greater change in velocity. Ta-da! 26. My problem with this is it like mentions a halfback and then like this other guy. And then like specifies the halfback, but then you like miss who's... I labeled it. Hopefully this picture helps you. In this picture, we are actually trying to find the initial velocity of the player, not the final. We know the final when they move together. And the big idea for these types of problems is conservation of momentum. The total momentum in the before picture is equal to the total momentum in the after picture. So let's do the total momentum of each object first. Hold on, must have light. There we go. So halfback is running to the right, has some sort of velocity, I just don't know what it is. Other player, opponent, is running to the left. They have a negative velocity. So 120 times -4. And the total momentum after would be both people together, so 210 kilograms at -2, meaning the total momentum in this problem is 420, but negative. 420 Newton seconds of momentum is pointing to the left. The total momentum in this picture is known. That must mean there's -420 Newton seconds of momentum in the final picture. But this means I have numbers I can solve. Let's see, I can add the 480 to the right, making something like 90 VI. equals 60 by adding 480 to negative 420, so that the velocity is 9/6. How about we write that as 0.6 meters per second to the right. Okay, impulse acting on halfback during collision. So we're only picking the halfback. We're calculating the impulse using the impulse momentum theorem. I don't know the force, so I can't just do force times time. I don't have a graph. So I'm going to get their initial and final momentum and just subtract them. Even though they stick together, I only want to use the 90 kilogram halfback mass. So their final velocity is -2. Their initial velocity was 0.67. And I should check for logic at the end of this problem. At the end of this problem, I should have a negative impulse acting on the halfback because the force applied during the collision is pushing the halfback left. So this would be 90 times -2 minus 90 times times 0.67. So a negative 240 Newton-second impulse. Now let's just go over the difference between total momentum and impulse. The total momentum tells you how much momentum is in each picture. Conservation of momentum says if it's 420 in the end picture, it must have been 420 in the beginning picture. But what impulse is saying is 240 is transferred from object to object. So my two objects transfer momentum, one to the other, still keeping it at 420 total. Get excited, we're almost done here. Hopefully you got to skip around to the parts you actually had trouble with. In this problem, we did a similar one in class. Please note that this one guarantees safety of the astronaut no matter what. Because the astronaut and astronaut and wrench are stationary to start, that means the initial momentum in this picture is 0. The final momentum in this picture is 0, and that's achieved by the fact that the 2 kilogram wrench at 10 meters per second has equal and opposite momentum to the astronaut. Please notice that for superelastic collisions, these should have equal and opposite change in momentum because they have equal and opposite impulses, because they have equal and opposite forces. So let's do this method. We have 0 momentum to start in the first picture. That leads to a negative momentum for the astronaut and a positive momentum for the wrench. 0 equals 85 VF plus 2 times 10. And I can totally solve this problem. I'm going to subtract 20 to the left. Equals 85 VF. Divide 85 to the left, and VF gets to be negative 0.235 meters per second. And please just check here. The smaller object is going faster, has the larger change in velocity. The larger object has a smaller change in velocity. But they still experience the same force because Newton's third law. When the astronaut throws the wrench actually pushes the astronaut backward, saving their life, getting them to the capsule. And since no matter what velocity goes forward here would result in a negative velocity in the astronaut's safe no matter what, at least in this iteration of the astronaut wrench problem. Now this is an elastic collision. Elastic collisions are a little bit tougher to manage because you need to keep in mind all of the velocities. So I tried to draw that picture out for you. Someone was asking, like, how do I know velocity goes to the left? Well, I know velocity goes to the left because this is a light object hitting a heavy object in an elastic collision. Therefore, the small object rebounds. Just like if this were a car, a tennis ball would rebound off of it. So let's conservation of momentum this. We have mass times velocity of every object in the before and after picture. The original momentum would be 0.17 times 20 plus 0 equals 0.17 V. I'm just going to leave that as VF and come back to it in a sec. I expect that number comes out to be negative, but I'm not going to throw any extra negative signs in there. I don't have to. So 0.33 at 13.6 meters per second. And one of the reasons the numbers are a little bit funny is because we wanted them to be realistic. On the left-hand side, we see that there are 3.4 Newton seconds of momentum to start. And so I'm going to put a little note over here. 3.4 Newton seconds, this is my total momentum. The total in the before picture is 3.4. The total in the after picture should also be 3.4. But of that 3.4 that's in the after picture, 4 of them, how is that possible? 4 of them go into this ice block. Okay, well that's possible because that means when I subtract 4 to the other side, I get a negative velocity, which is what I expected. So that's good. At least I did that right. I get a negative momentum. So obviously the puck should have negative momentum. Its momentum is negative 1.08 equals 0.717 VF. Divide by 0.17 to get a final velocity of negative 6.4 meters per second left. Hey, just a quick note on how to make sure you actually get the points you deserve on these problems. In order to get the points you deserve, please make sure your picture has mass, velocity of every object that you know, and leaving it as VF for the object you don't know. When you go to calculate a velocity, I need to see this conservation of momentum equation. That's the physics part. If you just write me a bunch of messes of numbers, then I can't give you partial credit. You get a point for writing down MV once for each object, so please do that. You also get points for recognizing velocity is in meters per second, so please put in your units. Please put in your negative signs if it's going left. You can indicate left using the word or with a negative sign. Impulse on the hockey puck then. It asks for both. I'm going to make it so I only need to do one. Ice is going to be easier to do because there's only one velocity for the ice. So I'm going to take the final velocity of the ice and the initial velocity of the ice, use them to calculate their initial and final momentum, and subtract. So originally it was at rest, velocity 0. At the end, its velocity is 13.6. So how much momentum did the ice gain? Well, the ice gains 4.488 Newton seconds. Positive because it's gained. The ice gains this momentum. Okay, that means the hockey puck must have lost it. If it's got to equal 3.4 total before and 3.4 total after, and 4 is transferred from one to the other, well, that must mean the block of ice, the puck, lost 4.4 Newton seconds of momentum. Right? Now, this should totally make sense to you because they experience the same force for the same time, getting the same magnitude of impulse and in opposite directions. So guys, you have made it to the last problem. Congratulations to you. And the last problem is an easy one if you can read this graph. Please change your masses from grams to kilograms. I did that and labeled it on my graph. Now we just need to get the mass times velocity of each object and total, where we would add them up. So mass times velocity of cart A to start is 0.3 times 6. So that is 1.8. Cart B to start is 0 because it's at rest, making a total momentum of 1.8 Newton seconds. The final momentum should also be 1.8, but don't jump to conclusions. What if I steered you wrong? Let's just check. Cart A. Cart A is going to be 300 grams times 2, so 0.3 times 2, that's 0.6. Cart B is 0.6 times 0.2, or 0.6 times 2, that is 1.2, making 1.8 newton seconds total. So yay, it's conserved. Yes, and I'll fill this out in later so you don't have to watch me type. Based on the data, what type of collision is this? Some sort of collision where they have two different velocities to start and the same velocity at the end. That is an inelastic. They start apart and they stick together. So, let's talk about impulse then. Last question on here. Impulse is the change in momentum acting on any single object. And hey, I already calculated the initial and final momentum of A. The final momentum of A is 0.6. The initial momentum of A is 1.8. A lost momentum, which we should know at this point. A lost momentum because it slowed down, and it lost 1.2 newton seconds of momentum. That must mean B gained 1.2, which we can see pretty clearly. It goes from 0 to 1.2. B gains 1.2 newton seconds of momentum. So, describe the transfer of momentum. A loses 1.2 newton seconds of momentum to B. This causes A to slow down. B gains 1.2 newton seconds of momentum from A. This causes B to speed up. Hopefully that helps, and hopefully you got to skip around and find just the parts that were concerning to you. Please notice this key will be online and in more depth. I'll be able to fill out these answers where I kind of just left them as one word later. Thanks for watching. Bye.